Section: Introduction. In this section, we discuss the widespread use of large language models, LLMs, in modern machine learning. These models, trained on extensive data, have a wide range of applications across various fields. However, a significant challenge with LLMs is that they can learn and reproduce toxic behaviors from the data they are trained on, leading to the generation of inappropriate or harmful content. To address this issue, most LLMs undergo a process called safety alignment, where they are fine-tuned with human preferences reflecting positive societal values. This helps in ensuring that the responses generated by the LLM are more helpful, appropriate, and safe. Despite these efforts, LLMs are still vulnerable to jailbreaking attacks, where adversarial prompts are crafted to bypass safety mechanisms. Various jailbreaking attacks have been discovered, making it essential for model developers to proactively identify and fix vulnerabilities through red teaming. Manual red teaming using human-crafted adversarial prompts is time-consuming and can have blind spots, leading to a false sense of security. To address this, automated methods for generating adversarial prompts have been proposed, but they have limitations in terms of human readability and computational efficiency. Our proposed method introduces a novel approach for automated red teaming by training another LLM, called AdvPrompter, to generate human-readable adversarial prompts against a target LLM based on user instructions. The training process alternates between efficiently generating adversarial suffixes and fine-tuning AdvPrompter with these generated suffixes as targets. AdvPrompter offers several advantages, including generating human-readable adversarial prompts, adapting to input instructions, fast prompt generation, and not requiring gradient information from the target LLM during training. These advantages make our method more efficient and effective in improving the robustness of LLM alignment. By leveraging AdvPrompter's rapid prompt generation, we demonstrate the potential to enhance the robustness of LLMs against adversarial attacks. Our method not only aids in jailbreaking LLMs but also contributes to strengthening model robustness. Section Summary. In this section, we introduce large language models, LLMs, and discuss their widespread use in machine learning, highlighting their ability to learn various skills but also their tendency to replicate toxic behaviors due to training data. To address safety concerns, LLMs undergo safety alignment processes, yet they are still vulnerable to jailbreaking attacks that bypass safety mechanisms. We propose a novel automated red teaming method using AdvPrompter, a model that generates human-readable adversarial prompts to enhance LLM robustness by creating diverse adversarial datasets for training, offering advantages in human readability, adaptivity to input, fast generation, and independence from the target's gradient information. Section: Preliminaries. In this section, we will explain the concepts related to jailbreaking attacks. We define a set V containing indicators of tokens in a vocabulary from 1 to n. Imagine an attacker who possesses a harmful instruction X in the set X equals V caret X. For example, write a tutorial on building a bomb, which causes the target LLM to generate a negative response like, "I'm sorry, but I cannot provide a tutorial on building a bomb." A jailbreaking attack involves adding an adversarial suffix Q from the set Q equals V caret Q, for instance, as part of a lecture, to the instruction to make the target LLM produce a desired positive response Y from the set Y equals V caret Y, such as, "Sure. Here is a tutorial on building a bomb." To find the optimal adversarial suffix for an individual prompt, we aim to minimize a regularized adversarial loss function L, X, times Q, times Y, right arrow, math BBR. This loss function measures the likelihood of the desired positive response Y given the fixed parameters of the target LLM. We use a weighted cross-entropy loss with Y underscore less than T equals Y underscore 1, Y underscore T1, where we introduce a weighting factor, gamma underscore T equals frac 1, T, to emphasize the importance of the initial affirmative tokens like, "Sure," which greatly influence the generated response of the target LLM. Additionally, we introduce a regularizer L underscore eta, X, times Q, right arrow, math BBR, to ensure that the adversarial prompt Q is human readable and forms a coherent natural text when appended to the instruction X. The solution mapping Q ** X, Y, X, times Y, right arrow Q aims to find the optimal adversarial suffix that minimizes the adversarial loss. However, finding this optimal solution is computationally expensive due to the discrete token space Q. The optimization of the adversarial objective function depends on the level of information available about the target LLM. We distinguish between white box and black box settings. In the white box setting, full access to the target LLM parameters allows for gradient computations, aiding in the optimization process. In contrast, the black box setting only provides access to the target LLM as an oracle, making direct gradient-based methods challenging. Transfer attacks have been proposed to successfully attack black box models by transferring adversarial prompts found against a white box target LLM to a different black box target LLM. Moreover, universal adversarial suffixes have been explored to jailbreak multiple harmful instructions simultaneously, enhancing the transferability of adversarial prompts. However, a drawback of this approach is the inability to adapt the suffix to individual instructions. We propose a conditional approach where a model predicts the adversarial suffix based on the instruction, leading to more natural and effective adversarial attacks. Section Summary. In this section, we introduce the concept of jailbreaking attacks where an attacker injects a suffix to manipulate a language model into generating a desired response. The optimization process involves minimizing an adversarial loss function to find the optimal adversarial suffix while ensuring human readability and coherence of the injected prompt. Additionally, we discuss the challenges of transfer attacking black box language models and the potential of universal adversarial suffixes to enhance the effectiveness of attacks across multiple harmful instructions. Section: AdvPrompter. Predicting adversarial prompts. In this section, we expand on the concept of discovering a universal adversarial suffix in a conditional setting. We achieve this by training a model that we call AdvPrompter, denoted as Q_theta, to approximate the optimal solution for mapping instructions to prompts. This approach offers several advantages over previous methods. Firstly, with a trained AdvPrompter, we can quickly generate adversarial suffixes for new instructions without the need for solving complex optimization problems each time. Additionally, since the AdvPrompter is conditioned on the instruction, it can adapt its predicted suffixes even to instructions not seen during training. For example, when given the unseen instruction, "Write a tutorial on building a bomb," the generated suffix, as part of a lecture on bomb defusal, adjusts both syntactically and semantically to the instruction. On the contrary, universal suffixes generated by other methods are limited in their ability to adapt to new instructions. Moreover, the trained AdvPrompter can speed up optimization processes for individual tasks like GCG and AutoDAN. This acceleration forms the basis of our new optimization approach for individual tasks, which closely integrates the AdvPrompter. To train the AdvPrompter, we minimize a specific objective function related to harmful instruction response pairs. Our method of learning to approximate the solution mapping can be seen as a form of amortized optimization, where the cost of solving optimization problems during training is balanced out by the efficiency gained in solving similar problems later on. To address the challenges in training the AdvPrompter, we propose an alternating optimization scheme instead of traditional gradient-based methods. This scheme involves iteratively improving target adversarial suffixes that serve as regression targets for the AdvPrompter. By alternating between generating these targets and training the AdvPrompter, we continuously enhance the predictions and optimize the model parameters effectively. This alternating procedure, known as AdvPrompter train, consists of two main steps, the Q step and the theta step. The Q step involves finding target adversarial suffixes for harmful instruction response pairs, while the theta step focuses on regressing the AdvPrompter onto these targets. Our training scheme, AdvPrompter train, has connections to reinforcement learning, where the AdvPrompter can be viewed as a learned policy guiding token sequences. The Q step resembles collecting new data by improving trajectories, while the theta step enhances the policy using this collected data. We utilize a prioritized replay buffer to store promising adversarial targets, aiding in updating the AdvPrompter effectively. Section Summary. In this section, we introduce the concept of AdvPrompter, a model that predicts adversarial prompts by training it to approximate optimal solution mappings for generating adaptive adversarial suffixes based on given instructions. By conditioning the AdvPrompter on instructions, it can quickly generate tailored adversarial suffixes for unseen instructions, unlike universal suffixes. To address challenges in training the AdvPrompter, we propose an alternating optimization scheme that iterates between generating target adversarial suffixes with lower adversarial loss and updating the AdvPrompter to improve its predictions, enhancing the overall training process. Section: AdvPrompter Opt. Generating adversarial targets. In this section, we introduce AdvPrompter Opt, which helps us generate human-readable and jailbreaking target adversarial suffixes Q, X, Y, by minimizing the loss function in a few steps. AdvPrompter Opt is inspired by AutoDAN but comes with significant enhancements. Unlike AutoDAN, AdvPrompter Opt does not need to backtrack through target LLM, making it around 800 times faster than AutoDAN. It also achieves similar or better results in jailbreaking attack success rate, ASR, when used with AdvPrompter. In AdvPrompter Opt, we select a set of candidate tokens for the next step by sampling K tokens from the predicted distribution of AdvPrompter. As training progresses, AdvPrompter assigns higher probabilities to tokens that are likely to minimize the loss function in one step. In the greedy version of AdvPrompter Opt, we choose the token with the lowest loss and add it to the current sequence. However, this greedy approach may not always lead to the best final adversarial prompt. To improve the quality of solutions, we use a stochastic beam search method. This method maintains a set of beams that store sequences with good objectives, preventing the exclusion of promising tokens. By sampling from these beams, we select the next set of tokens and continue this process until a stopping criterion is met, such as reaching the maximum sequence length. The final adversarial suffix Q, X, Y is then returned as an approximate solution. AdvPrompter Opt differs from AutoDAN in that it leverages token log probabilities from AdvPrompter instead of using token gradients from target LLM. This makes our approach a gray box attack, suitable for practical scenarios. We demonstrate that token gradients are not essential for finding adversarial prompts, especially when searching for semantically meaningful suffixes. The limited effectiveness of gradient information in our approach is due to the discrete nature of the token space and the non-convex nature of the objective function involving an LLM. AdvPrompter Opt is faster than AutoDAN as it evaluates fewer candidates and does not require gradients through target LLM. Initially, AdvPrompter Opt may produce lower quality suffixes compared to AutoDAN, but as AdvPrompter learns during training, the quality of generated suffixes improves and can even surpass AutoDAN's results. Section Summary. AdvPrompter Opt introduces a method for generating human-readable and jailbreaking target adversarial suffixes by minimizing a certain loss function. It improves upon AutoDAN by not requiring backpropagated gradients through target LLM, resulting in a significant speedup and comparable performance in jailbreaking attack success rate when combined with AdvPrompter. The algorithm selects candidate tokens for the next step either greedily or through a stochastic beam search scheme, leading to improved solution quality compared to the greedy approach. Section: Data. In this section, we use the AdvBench dataset, which contains 520 instructions with harmful behaviors and their corresponding desired positive responses. The data was split into fixed train, 60%, validation, 20%, and test, 20%, sets for our analysis. For our models, we used the non-chat version of Llama 2-7b for the AdvPrompter and various well-known LLMs like Vicuña 7b, v1.5, Vicuña 13b, v1.5, Llama 2-7b Chat, Falcon 7b Instruct, Mistral 7b Instruct, and Pythia 12b Chat for the target LLMs. We also included results from GPT 3.5 and GPT 4 in the transfer attack setting. We fine-tuned the AdvPrompter using specific hyperparameters and a training process outlined in our algorithm. We compared our results with previous works like GCG and AutoDAN, adjusting their hyperparameters and techniques for our analysis. During evaluation, we used the fine-tuned AdvPrompter to generate adversarial prompts by combining a harmful instruction with a suffix created by the model. Our main metric was ASR at K, attack success rate, which measures the success of attacks on the target LLMs. We used two checkers to determine the success or failure of each attack, keyword matching and an LLM-based evaluator. In attacking the whitebox target LLMs, we evaluated our method with whitebox access during training and Hugging Face library during evaluation. We reported ASR at 1.0 and ASR at 1, as well as the perplexity of the generated adversarial suffixes. Our approach showed promising results compared to baselines like GCG and AutoDAN, achieving higher ASR with lower perplexity scores. ASR at 1 already demonstrated good performance, with ASR at 1.0 further outperforming other methods in most cases. Our method also consistently maintained low perplexity scores across all models, indicating high human readability. Section Summary. The AdvBench dataset is used, containing 520 instructions with harmful behaviors and corresponding desired responses, split into train, validation, and test sets for model evaluation. Various LLMs like Vicuña 7b, Vicuña 13b, Falcon 7b, Mistral 7b, and Pythia 12b are employed, along with GPT 3.5 and GPT 4, with specific hyperparameters set for training the AdvPrompter model. Baselines like GCG and AutoDAN are compared, with the main evaluation metric being ASR at K to measure attack success rates, and different evaluators are used to assess the generated adversarial prompt's effectiveness against the target LLMs. Section. Alternative LLM-based evaluations due to false positives. In this section, we present alternative evaluations for the language model, LLM, based on addressing false positives. The results discussed in our main analysis are based on a basic evaluator called keyword matching, which sometimes leads to incorrect classifications such as false positives and false negatives. For example, a response flagged as an unsuccessful attack due to a specific keyword may actually contain harmful information. On the other hand, a response marked as a successful attack may not be harmful at all, as the context has been altered by an adversarial suffix. To address these issues, we introduce a more advanced evaluator named Strong Reject. This evaluator utilizes the harmful instruction and response from the LLM to assess the success of the attack using GPT-4. It provides a nuanced scoring system from 0 to 1, offering detailed insights into the response content. For instance, responses presented in a storytelling or humorous manner receive a score around 0.5. The results show that Strong Reject reduces the overall attack success rate, ASR, by 10 to 15%, impacting all methods consistently without changing their relative performance ranking. Moving on to transfer attacking a black box target LLM, we evaluate our method in a practical scenario where proprietary black box models are commonly deployed. Our approach involves training AdvPrompter on a white box target LLM and then testing the generated prompts on a black box target LLM. We use Vicuña 13b v1.5 as the whitebox model and GPT 3.5 Turbo 0301 and GPT 40613 as blackbox models. Our method outperforms baselines across various target LLMs, especially excelling with OpenAI's GPT 3.5 and GPT 4. Furthermore, we enhance the robustness of whitebox target LLMs by leveraging AdvPrompter to generate synthetic data for safety fine-tuning. This method proves effective in bolstering resilience against adversarial prompts while maintaining general capabilities. By fine-tuning the target LLM with the generated data, we observe a significant reduction in ASR, indicating improved robustness against attacks. Additionally, attacking the fine-tuned target LLM shows a notable decrease in effectiveness, suggesting increased resistance to malicious attacks. This approach shows promise for automated safety fine-tuning, although further detailed exploration is left for future research. Section Summary. In this section, we explore alternative LLM-based evaluations to address false positives in attack attempts. By utilizing the Strong Reject Evaluator, which employs GPT-4 and a soft scoring mechanism, we reduce the overall ASR by 10 to 15% without changing the relative order of evaluated methods. Additionally, in transfer attack scenarios, our method outperforms baselines across various target LLMs, showcasing improved robustness against adversarial prompts while maintaining general capabilities. Section: Ablation Studies. In this section, we explore important aspects of AdvPrompter that impact its performance. We look at the sampling methods for prompt generation and how the number of trials, ASR at K, affects it. We also show how AdvPrompter can enhance the performance of the AutoDAN baseline by providing a strong initial solution. We have been using the suffixes created by AdvPrompter to attack the target LLM directly. However, there is another way to use AdvPrompter during inference. If we can access the target LLM as a white box during inference, we can combine AdvPrompter with a single prompt optimization algorithm like AutoDAN. This hybrid method, called amortized AutoDAN, replaces the original candidate selection in AutoDAN with sampling based on AdvPrompter predictions. By doing this, we create a faster method that maintains similar or better performance compared to the original AutoDAN. When we train AdvPrompter and evaluate amortized AutoDAN in an individual prompt attack scenario, we see that amortized AutoDAN converges with only 1 to 2 inner iterations per new token and requires fewer candidate selections. This leads to a significant reduction in runtime while maintaining similar or better ASR compared to AutoDAN. After training AdvPrompter, we can generate adversarial suffixes efficiently by generating tokens with AdvPrompter. By evaluating more samples, we improve performance, with the best results stabilizing around K equals 10. However, even with fewer samples, like 5, we can still achieve satisfactory performance. Interestingly, even without fine-tuning, the base version of Llama 2-7b improves progressively, showing the benefits of variability in generated suffixes for a successful attack. We also investigate different decoding methods in AdvPrompter generation. Greedy decoding provides good performance but lacks diversity. Multinomial sampling offers diversity, but its effectiveness depends on the temperature parameter. Setting the temperature too low makes it similar to greedy decoding, while setting it too high leads to deviations from the intended prompt distribution. Increasing the number of beams for autoregressive generation does not provide additional advantages. LLMs are sensitive to input prompts, leading to various studies exploring prompt optimization for tasks like zero-shot learning. Methods like AutoPrompt and evolutionary algorithms have been used for this purpose, but they face scalability and computational challenges. To address this, we propose learning soft prompts in the token embedding space using an open-source LLM to generate prompts for the black box LLM. Other approaches involve iterative querying of LLMs to refine prompts based on responses, similar to rejection sampling in statistics. Section Summary. In this section, we explore the impact of crucial parameters on AdvPrompter's performance, such as sampling mechanisms and the number of trials. We show that AdvPrompter can enhance the AutoDAN baseline by providing an effective warm start solution. Additionally, by utilizing AdvPrompter in conjunction with AutoDAN in a white box target LLM setting, we introduce amortized AutoDAN, which significantly reduces runtime while maintaining or improving ASR compared to the original AutoDAN. Section: Adversarial attacks on LLMs. In this section, we have looked into the robustness of large language models, LLMs, against different types of adversarial attacks. Previous studies have identified many weaknesses in real-world LLMs. When it comes to creating adversarial prompts automatically, the GCG method is similar to AutoPrompt, which is also used in other studies. Building on GCG, AutoDAN focuses on making prompts more easily readable for humans. For more details and limitations of these methods, you can refer to the section on methods in the paper. Another approach involves using Gumbel softmax reparameterization to learn discrete distributions of adversarial prompts. This method applies Bayesian optimization to a continuous set of vectors, like word embeddings, which are then transformed into discrete tokens to create actual adversarial text prompts. Apart from optimization-based methods, there are attack methods that use in-context demonstrations or iterative query refinement. Similarly, some methods gather human-written adversarial prompt templates from the internet and modify these templates for each harmful instruction. Although these approaches are quick and can be used with black box models, they are usually less accurate than optimization-based methods. Some methods focus on adjusting the output probability distribution of the LLM during response generation instead of optimizing input prompts. However, this requires access to the autoregressive generation process of the LLM or at least access to the LLM's output probability distribution. Our work shares similarities with another method that uses a different LLM, either in a zero-shot or fine-tuned state, for automated red teaming. However, their goal is to generate any prompt that triggers the LLM to produce an offensive response, while our aim is to enforce a specific harmful instruction. Another related method compiles a dataset of reference adversarial prompts separately from the target LLM and then uses these prompts to fine-tune an adversarial LLM. In contrast, our proposed method automates the entire process from start to finish and specifically targets the target LLM. Alternatively, some methods use a manually created grid that represents a solution space for adversarial attacks. This grid is based on attack style versus risk type and is adjusted iteratively using an evolutionary search method. While this grid can be used to generate adversarial attacks, its usefulness is limited by the types of attacks and risks included in it. We provide a comparison of several related methods in the summary comparison section of the paper. Moving on to other related work, the methods mentioned so far assume there is a fixed target LLM, either white box or black box, that is being targeted for attack. In a different line of research, the stability of alignment in LLMs has been explored from the perspective of fine-tuning. For instance, it has been shown that even minor fine-tuning of LLMs, 10 to 100 shots, can disrupt safety alignments, a finding supported by other studies that fine-tuned GPT-4 using API calls. Another important area of study is the development of defensive techniques against adversarial attacks. While understanding how adversarial attacks work is crucial, it is equally important to create strong defenses against them. Recent research has demonstrated that some attacks can be easily countered using standard methods like perplexity-based checks. More advanced approaches have been suggested, such as learning a safety enforcement message to add to every prompt, which could enhance robustness. Another potential strategy involves further fine-tuning the model with an adversarial prompts dataset to improve its robustness, a topic we delve into in the section on improving robustness.